So the question we kind of wanted to answer was, how do catalysts increase reaction rate? And before I can answer that, I'm going to have to give you a brief introduction to enthalpy, and I promise it's related. But basically, we need to firstly, and this will be quite brief, we'll be talking about it more in sort of later weeks, but basically get the idea that enthalpy represents the sort of chemical potential energy. So you understand that energy can only be transferred or destroyed. So into other, can neither be, created or destroyed, only transferred from one form to another, of which chemical potential energy kind of is one. And so if we burn wood and get energy out, so if we combustion of wood is exothermic. And what that means is, for example, we take wood, it reacts with oxygen, we burn it, and you get carbon dioxide and water in the ideal case. But we also have this energy, right? That's released. Now, this energy that's released, where does it come from? If energy can neither be created or destroyed, where does this energy come from? Well, remember, it can't be created or destroyed, it has to be transformed. So we need to think about where did it get transformed from? And since we're taking wood and oxygen and burning it to get carbon dioxide and water, it's basically chemical potential energy to heat energy. So it's transformed from the chemical potential energy. And this chemical potential energy, you can think of as split into your reactants, which have some chemical potential energy, and your products. Does that make sense?
Yeah.
So your reactants will have some chemical potential energy, and your products will have some chemical potential energy. And given that, now, and we've got this energy given off as well, right?
Yes.
So do you think the chemical potential energy of the reactants or the chemical potential of the products, which one's higher in this situation?
Of product. Oh, I mean of reactants.
Yeah, the reactants must be higher because for the reactants to be able to lose, I mean, they would have to lose potential energy to give some off, right? So once they've lost some and become the products, that means this is the reactant level. And think of it like falling down a slope or something, then this is the product level, right?
Yes.
And so we actually call this H for enthalpy. So capital H represents enthalpy, and this is the reaction. And a lot of the time, we just represent it like this, especially at the start. So we'll notice that this level here is delta H, and that is negative. So delta is changing, finest minus the initial. So that means we lost chemical potential energy, or, delta H, which is enthalpy. Change in enthalpy is negative. That means this is exothermic. All right?
Yeah.
So that's the basic idea behind enthalpy, that enthalpy changes, right? If the enthalpy change is negative, that tells you it's exothermic. And if the enthalpy change is endothermic, that tells you it's exothermic. So that's your first basic idea, that enthalpy represents chemical potential energy. And when you get a reaction occurring, you might have reactants here, products here. This is a situation where delta H is negative, which means it's exothermic. That means somehow it went from that level to that level. Conversely, you could have reactants starting here, and you end up with more potential energy. And so basically that went up, and that means your delta H is positive, and that this is endothermic. Are you happy with that?
Yeah.
Now here's the thing though, that's too simple. It's not wrong, it's just too simple. because it doesn't go like that. It doesn't go like that. It doesn't go in a straight line like that. What actually happens is you have a hill in the middle. And so you need to kind of gain energy first before you can go down, even if it's exothermic. And this here is the required energy input, and we give it a name called activation energy. So a more complete version of this is instead of having that red arrow just represent the start and the end, there is a middle that we need to consider.
Yeah.
And it might be helpful to recognize that only the start and end matter for delta H right? You went from reactant to product, but only this here is EA. This here is EA. And EA is the activation energy. Does that make sense?
Yeah.
Which is the amount of energy required for, the reaction to proceed. That clear so far?
Yeah.
So think of activation energy like a cost, like an initial cost, right? If this even though you get a net gain, you still need to pay an entrance fee, right? And this one, the entrance fee is higher than your gain, so you lose money overall, kind of thing.
Yeah.
So let me ask you: if the activation energy is high, is it easy to do? Activation energy is the amount of energy you need. So if that energy requirement is very high, is that easy to achieve?
No.
No, it's not. It's going to be difficult to achieve. So whether how easy it is to achieve or not depends on how large or small the activation energy is, right? You agree, if the EA is high, harder to achieve. If EA is small, easier to achieve, correct?
Yeah.
And that's where the catalyst comes in. The catalyst lowers the activation energy. Which means with a catalyst, you still start and end up at the same spot, but you now have a lower EA.
Yeah.
And that basically is how a catalyst increases the reaction rate.
Okay.
Now, what we'll be considering next time is how do catalysts do that?
Okay.
How do they reduce EA? And that will basically go into your next module. And that's basically what we're looking at going forward.
Yeah.